So today we're going to talk about polar curves, or polar coordinates and then polar curves. So, probably all of you have seen polar coordinates to some extent before. So polar coordinates are a way to put a different coordinate system on the plane that is more convenient for certain situations, and it works as follows. So we're going to take the positive real numbers, like this half line here, from 0 to positive infinity, and for any point in the plane, say this point, we consider the angle between the line that goes to 0 and the point we're interested in, and the positive real numbers, this angle here. Okay, so note we're counting the angle going anti-clockwise. And this is one of the coordinates we require, and the second coordinate is the distance from the origin. That gives us two coordinates. We have the angle from the positive real numbers, and we have this distance away from the origin, right? Those are polar coordinates. So this is our point, theta, right? And this is a way to give coordinates to every single point in the plane, right? Every single point in the plane can be described by an r and a theta, where theta is going to be between 0 and 2 pi. So theta belongs to 0, 2 pi, not including 2 pi, because if we do 2 pi, we're going back to 0, right? And initially, we're going to take r bigger than 0, where it's the distance away from the origin. And this system of coordinates is extremely efficient and very, very useful in certain situations when you have something called rotational invariance, when we rotate the object or rotate the mathematical object and it remains the same. So this is a very useful coordinate system, and it's one which we want to be able to do calculus on, right? We're doing calculus with respect to x and y. Now we've learned about parametric curves. We're later going to see that this, in a sense, is an example of something that where we can use these techniques for, and we're going to learn to do some calculus with respect to r and theta, okay? With respect to defining function, with respect to r and theta. So we start with some initial warm-up questions. So this is example 2. Consider the point in polars given by 2 pi over 3. Find its Cartesian coordinates, which means find its coordinates in terms of x and y. Okay, so let's draw a picture. And I recommend you do this for all these questions. We have that the radius is 2 and the angle is pi over 3. So pi over 3 is something like this. Okay, this is pi over 3. And the radius is 2. So this is our point here. Oops. Two pi over 3, right? And then we ask ourselves, what's the x and y coordinate of this? Well, the x coordinate is whatever this is, and the y coordinate is whatever this is, right? Yeah, and we can find them just by trigonometry, right? Because we have the radius and we have the angle, right? So this is the adjacent side of this right angle triangle. So this thing has to be given by 2 cosine pi over 3, and this thing has to be given by 2 sine pi over 3. Yeah? cool. So that's all we need to do. So we're going to have 2 cosine pi over 3, which is just a half, 2 sine pi over 3, and that turns out to be just 2 times 1 over 2, and then 2 times root 3 over 2, so that's just equal to just 1 root 3. And those are the x and y coordinates of our guy, right? So this is the x coordinate, this that we now know is 1, and this is the y coordinate, which we now know is root 3. Yeah? All right, so I hope this is fairly straightforward and probably isn't new for you. So thumbs up if you've seen this kind of thing before. No? Okay. Okay, some people. Most people. All right, good. So that's how we can go from polar coordinates to Cartesian coordinates. We can go the other way around, right? So there's example 3. Represent rep one comma minus 1 in polars. Okay, so we are going to find the arm, the theta that represents this. Again, draw a picture. So 1 comma minus 1. So that means we are 1 in the x direction, minus 1 in the y direction. So we're like here. This is 1 minus 1. No? So we're going to have to find this angle here, and then this radius here. Yeah? Okay, so a couple of caveats. Sometimes it's more convenient, as you see in this example, to instead of going anti-clockwise from the positive real numbers, to go clockwise from the positive real numbers in the opposite direction. And if we do that, then we say we can do that so long as we specify the angle as negative, right? So if the angle is positive, then we're going clockwise around like this. But if we decide to go in the opposite direction, then we say the angle is negative. And we can represent the angle with either the positive number going anti-clockwise from the positive real numbers, or a negative number, which means we go clockwise. Yeah? So if we decide to go anti-clockwise, the long way around, right? Let's think about what angle we have here. Well, if we go from here to here, that's pi, right? And then from here to here, it's 3 pi over 2 right here. But we have another thing here. We have to add another quarter to it. Yeah? So if we go clockwise, then the angle, sorry, anti-clockwise, then the angle is 3 pi over 2 plus this quarter pi, right? So that's the same as 7 pi over 4. Yeah? But if we go clockwise, then it's a shorter distance, and now we're just going minus pi over 4. Yeah. So this distance here is minus pi over 4, and this distance around here is 7 pi over 4, and that's it. Yeah. So cool. Now we need to know what the radius is. So what radius do you see here? What r are we going to put? This is our point. What's this length here? Square root of 2. Yeah, just as by Pythagoras, right? We have a right angled triangle. Yeah. So the length of this thing is this thing squared plus this thing squared, square rooted. Yeah, which is root 2. Yeah. Thumbs up if that's clear to you. Thumbs down if it's not. Okay, cool. So in polars we have square root of 2, and then if we choose to do the anti-clockwise angle, we can write it like this, or we can write square root of 2 and minus pi over 4. And it's perfectly unambiguous to do this, right? Because we know what we mean when we do positive angle, we're going anti-clockwise. We know what it means when we have a negative angle. So this two things mean exactly the same thing, and it's completely unambiguous. All right. Everybody happy so far with this? Yep. So this is how we go backwards and forwards from these things. So in Euclidean space with Cartesian, in Cartesian space, we're used to describing curves like this, right? So a curve in Cartesian space would be defined by a graph like y of x equals something, right? Or x of y is equal to something like this, yeah? And if we're going to have a curve in polar coordinates, then we're going to have something similar, except now our variables are the angle and the radius, right? So an example, one of the things we can actually have is r of theta is something depending on theta, right? Yeah. Or we could have theta is something depending on r. But that's much rarer because we have less interesting ones. So this is the main kind we're going to think about. But sometimes we're going to have theta is what is actually defined. Let's think about r of theta first. So let's do this. This is example 6. What if we have r of theta is equal to 2 cosine of theta? Yeah? All right, so before we do this, there's another useful convention. So I've defined so far polar coordinates when you have a positive r, right? And we've learned now that we can have a negative or positive angle, right? Again, positive means anti-clockwise, negative clockwise. Sometimes we want to deal with negative r, right? So we define for r bigger than 0, minus r of theta to be r of theta plus pi. So what does it mean? It means that if we have a negative theta, or negative r, so suppose this thing, so minus r theta, then we define it to be the point which is actually completely on the opposite side from 0, right? This point here, right? So if we add pi over 2 to this thing, then we'll take it right over here, yeah? It'll send it right over here, yeah? So this thing actually is what we think of as being this thing right here. Let me say that better. So this is r of theta. Then if we add pi over 2 to this thing, then we end up here, which is r of theta plus pi, like this. Okay, so whenever we have a negative r, just think about what would happen if we have a positive r and we just took the mirror image on the opposite side of 0. Mirror image is not the right word. It is a reflection through 0. Just think about what happens if we just take the reflection through 0 on the opposite side of 0. Okay, that's what we mean when we have a negative r. Right? And it sort of makes sense because if positive r is going this way, then negative r should be going the opposite way. Okay. And it's just a convention. We have the right to define this. We haven't defined what it means to have negative r theta yet. So we have the right to define it this way. Right? And that's what we choose to do. And if we do this, then something like this actually makes sense because, as you know, theta, for various branches of theta, cosine is going to have positive and negative values. Yeah? Cool. So this is our guy, and what we're asked to do is to sketch this graph. So let's make a sentence. So let sketch r of theta. And this is one of the harder things you're going to have to learn. Okay, solution. First thing to do is to draw a graph of cosine just to have it to refer back to, right? So what does cosine do? It goes like this, goes like this, and it goes like this. Yeah? So this is pi over 2. This is 3 pi over 2. And this right here is just 2 pi. Yeah? So it's graph of cosine. All right, so to sketch this thing, let's draw xy plane. And what happens? So as theta varies, the radius is changing with respect to theta, right? So we're plotting all the points. So plotting given by r of theta, right? So at last resort, you could just take a bunch of points theta, find what the r of theta is, and just plot it around like this, right? But as you get better with this kind of stuff, you'll be able to do this more and more in your head. So we're going to start with the kind of strategy which is analogous to that. We are going to refer back to this graph, and we're going to try and plot what this thing does as we let theta go from 0 to 2 pi, and then 2 pi to pi, and then pi to pi over 3 pi over 2, and so on, yeah? All right, let's go for it. Let's start. So when we have theta equals to 0, where are we starting? Where are we starting in this case? Theta equals 0. Just plug in theta equals 0 into this thing, right? So in this particular case, it's given by 2 cosine theta, 0. Where are we starting when theta equals 0? Yeah, starting at 2, 0, right? Because the radius is 2, the angle is 0. So we're starting on the positive real numbers at 2, 0. So we start here. Yeah? And that is, let's put it underneath. That is equal to r of 0, 0. Yeah? Cool. All right. Now, so this is the angle we have. Now, as we increase theta, and we're going from 0 towards pi over 2, what is happening to the radius? So we're going along like this. What's happening to the radius given that we have this polar curve? It's decreasing, right? So at every angle, whatever this angle is, we're going to be plotting the r of theta along here, right? This is the r of theta. Let me put it over here. So this is our r of theta. We're going to be plotting, right? And as the angle increases towards pi over 2, then we're plotting something which has got smaller and smaller radius, right? So we can see in our minds that what is this going to look like? As we let the angle change, then the length of this radius is decreasing, 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 decreasing like this, yeah? Do you see what I mean? Give me a thumbs up if so. Good. So, we could, as I said before, just take various angles and plug in what r of theta is. But, okay, that means no, it's not so bad to do that. Let's, for example, take the angle given by pi over 4. Right? So if this is pi over 4, then this is where we are. Yeah? So then the radius will be cosine of pi over 4. Yeah? Yeah, and let's remind ourselves what that is. So we have pi over 4, then both sides are the same, and so 1 here, and then this is root 2. So we know that cosine is 1 over root 2, right? Because it is the adjacent side divided by hypotenuse. So let's plug it in right here. So this is the angle pi over 4, like this. And now we have something shorter because it's 1 over root 2. So it's like something like here. So this would be the point 1 over root 2 pi over 4, right? Which corresponds to what happens when we are taking the angle right here. And this here is our radius. Yeah? So if we took the angle somewhere close towards pi over 2, we'd see the radius is even smaller. Yeah? Yeah? Cool. And when we actually hit pi over 2, which is this angle, right, then the radius is actually 0. Yeah, the radius is actually 0. So if we're just a little bit before pi over 2, suppose we're at this thing here, just a little bit before pi over 2, then the radius is really close to 0, right? So what we can sort of see from this is that we have this loop being sketched out, right? Like this, like this, like this, like this, like this, like this, like this. Because as we do this, and we increase the angle, the radius is decreasing, 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 decreasing. Are you with me, people? That's right. Yeah. Thank you. Yes, it's 2 over root 2. Sorry about that. 2 over root 2. Thank you. Very good. All right, so what we've done, we've plotted what happens to the angles you go from 0 to pi over 2. Yeah? And this angle right here, the very last thing we've drawn, is exactly when we have things in direction angle pi over 2, and it's got radius 0. Yeah? So if you zoom in here, it's actually going like, if you zoom into this little picture here, let's zoom in. What do we have? We have that it's looking like this, right? It's looking like this. Yeah? That's what we should see at this point. All right, now it's a little bit harder because we're going from pi over 2 to pi, and now we're going into the negative numbers. Yeah? All right, and we know when we do the negative numbers, it is what happens if we had a positive radius, but we flip it not mirror image, but we flip it across 0 to the opposite side. Now, my recommendation is that you don't do both things in your head at the same time. We do one, then the other. So what we're going to first do is we're going to plot it as if it was positive, as if the radius was positive, which isn't the real point that we want, but we'll plot that first, okay? So let me do this thing to indicate we're doing this part of the graph from here to here, yeah? And it's a negative radius, but we're going to plot it as if it was a positive radius. So what we're actually going to plot is the absolute value of r of theta, right? So plotting it as if r was positive, what happens? Well, if r was positive, then the graph actually looks like this, right? Yeah. So if we take the absolute value of cosine of theta, then it goes up like this. Yeah. Let's just emphasize this. This is absolute value of cosine of theta. So plotting now the absolute value of absolute value of cosine of theta, what happens? Well, if we do that, then we see that the radius goes from 0, and then it increases until we get to value pi when it's 1. So then we get 2, right? So let's try and plot it on this part. Again, we're not plotting the real thing we want, we're plotting a different graph, and then we'll get it, the one we want from it. So we're plotting 2 absolute value of cosine of theta, right? So as we have angles which are very close, a bit bigger than pi over 2, the radius is very small, right? But as we keep going, it gets bigger, right? And it's going to look something like this. And then when we hit the angle pi, we are here like this, yeah? So this is angle pi, and the radius will be given by now 2, yeah? And the angle is pi for this graph here. So this is this graph. Okay? But that's not the one we're asked to do. We're asked to plot this guy. Yeah? We're not asked to plot this guy, we're asked to plot this guy. But to understand what this thing is, we need to take this guy and remove the absolute value signs. And over this region, it's just negative, right? So when we remove the absolute value signs, we have negative whatever we have here. Yeah? So if we plot the actual guy, whenever we have whatever this angle is, if this angle is this thing right here, if this is our angle, then when we take the absolute value, then it's like somewhere like this. But the real guy we want is the reflection through 0 on the opposite side. Yeah? So the real guy we want is what happens when we reflect through 0 and end up here. Yeah? So let's call that one, I don't know. Let's not give it names, there's too much stuff here. This guy gets sent to this guy. And if we go here, right, whatever this angle is, then it gets reflected on the opposite side here. And if we go here, then it gets reflected on the opposite side here. And those points are the points that are actually on the graph that we want the graph of this thing. This is one of the trickier things you have to learn. Are you with me so far? Speak up if you're not, because we're going to have to use this lots of times. I mean, this is one of the key things. Replay this particular part if it isn't clear to you, and then talk with me in office hours if it's still not making sense. Huh? So when we actually plot, what happens is we go over this range of angles for the real graph that we want, where we don't take the absolute value, then it's going to be what happens when we take all these points and then just reflect them on through the origin here to the opposite side. So what we're going to see is actually this thing. Right? Because if we do the mirror image of every point through, not the mirror image, but the reflection through 0 of every point, we end up like this. So this guy gets reflected to this. Yeah? Cool. So what happens as we go from 0 to pi over 2? We go round like this. And as we go from pi over 2 to pi, we go back like this. Yeah? Yeah? Cool. And this thing we've just drawn is just an auxiliary help aid we've put to help us figure out what happens when we go into the negative numbers, the negative angles. Yeah? Well, the negative cosine of theta, and therefore the negative radii, not the negative angles. All right, cool. So when we are at pi, then we are actually here, right? So this is r of pi, comma, pi. Yeah, that's where we are. And, okay, maybe now it's worth putting in some things. So if we are, say, here, which is angle, say, 3 pi over 4, right? So this point here is absolute value of 3 pi over 4, comma 3 pi over 4, which isn't the thing that we want, but the actual thing that we want is its reflection through 0, which is actually here. This is r of 3 pi over 4, 3 pi over 4. Yeah? Cool. All right. If you're good with this part, then it gets easier because we're just doing the same thing. Now, we start from pi, and we're going to go to 3 pi over 2. Yeah? We are still in the negative numbers. Yeah? So again, my recommendation is that we don't plot the actual graph with the negative radii. We plot the one with the positive radii, and then we reflect it, so we don't try and do two mental things at the same time. So we're going to plot again this thing. We're going to plot again this thing. So if we are plotting two absolute value of cosine of theta as we go from here to here, right? Then we start with the radius 2, and we gradually decrease until when we are at 3 pi over 2, we have radius 0. Yeah? So doing that, we start with radius 2, and then as we continue to increase the radius from pi to 3 pi over 2, the radius decreases, 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 and it does something like this. Right? So this part, let me put little crosses here just to distinguish it from the other things. This part here is the part of absolute value cosine of theta for theta over the range between pi and 3 pi over 2. Yeah? That's what this part is. Yeah? But it's not the real thing. The real thing is when we don't have the absolute value of theta, we allow it to have the negative values. So if we do that, we're just reflecting again through 0. So this point gets reflected to this point gets reflected to this point, this point, to this point, this point, to this point, and so on. Yeah? So what we see happening is that the actual graph, now I put little circles to distinguish it, the actual graph of r of theta, as theta goes from pi to 3 pi over 2, does this loop, right? It loops around like this. Yeah? Thumbs up again if you're with me. Thumbs down if not. Huh? Okay. If you've never seen this before, this isn't particularly easy. You have to build your mental muscle to do this. So this is the part we've just talked about. This part of the graph, right? Okay. Well, I should perhaps better say this part of the range of theta, but no matter. All right, final thing. We're going to do from 3 pi over 2 to 2 pi. But now, happily, we are in positive angles. Start again. Yeah, we are in positive values of cosine, therefore positive radii. Yeah? So we don't have to worry about sketching the absolute value of r of theta. We can just plot it directly without this. Yeah? Cool. So when we did this, yeah, we ended up here. So this is where we were. We are here at 0. Well, let's write it in terms of theta. So this is r of 3 pi over 2, 3 pi over 2. Yeah? That's where we are. Yeah? And now we're going to do this part where we allow theta to go from 3 pi over 2 to 2 pi, and the radius is positive, right? So if we take something like this, which is just a little bit bigger than 3 pi over 2, yeah, that means we are somewhere along this line here, right? So this is all the points where in polar coordinates, the angle is given by 3 pi over 2 plus a little something, right? Yeah, and the actual radius is given by this length here, so we are going to be, say, here. Huh? And as we go forward a little bit, say to this thing, then we are going to be here. And you see what's happening. We are going from radius 0, increasing back to radius 2. Yeah. So let me do little triangles to indicate this is the part that we are now doing. And if we do this thing, then this is where we're going over. Yeah. All right. It's a very busy picture, right? But let's go again. What did we do? We go from 0 to pi over 2. That gave us this first half of the circle. Yeah. Then we went from pi over 2 to pi, and it was negative radii. So we made our life simple by thinking, okay, firstly, what happens if we take the absolute value of the radii? Well, that would give us this part here. But then to get the part when we have the negative radii, we reflect all these points, all this part of the curve through the origin. So reflecting this thing through the origin gives us this thing, which loops all the way back and completes the circle. Yeah? Thumbs up if you're with me now. Cool. So we are here. We're back to this thing. Now, this part, again, negative radii. We want to plot positive radii. So we plot positive radii. What happens? We start from here. We go down like this. Yeah? So the positive radii. So when we reflect it through the origin, that means doing this part, looping over the first thing again, the first half of the circle again. That's this thing. Yeah? And then the final part, we do this to this, but now we went positive radii. Positive radii, so no reflection necessary. Yeah? So we just directly take the angle and then the radius, and that gives us exactly this thing. Yeah? This is exactly this thing. All right, we have more to talk about. Obviously, leave whenever you want. We have another 3 minutes of class time. Okay, cool. All right, the second part of the question is to express this equation as a Cartesian equation, which means express it in terms of x and y. Yeah? Right, so if we did this, then what we would expect would be that when we express these things in terms of x and y, we should get something like a circle, because it looks like what we're looking at is a circle, right? It looks like we're looking at a circle. So let me try and put it on the same part, because I can keep the picture and... Okay, so how are we going to go from something in terms of r and theta into something in terms of x and y? Well, what relationships do we have? Well, we have that the radius by Pythagoras is going to be x squared plus y squared for sure, right? That's kind of a straightforward thing to figure out, right? Because the radius is the distance from the origin. So if we had this point, which is in terms of r and theta, also in terms of x and y, then for sure the radius has to be given by this in terms of x and y. Yeah? That's straightforward. Now we want to get some kind of a handle on the angle, right? So let's put this thing here, right? So for example, if we look at this side of this right angle triangle, then by Pythagoras, then this thing should be equal to r cosine of theta, right? And the opposite side should be equal to r sine of theta. Which gives us another relationship that we must have that x is equal to r cosine of theta and y is equal to r sine of theta. Yeah? Cool. So, in particular, cosine of theta is from this thing going to be, well, start again. Cosine of theta from this thing is equal to x over r. Yeah? And since we have r is equal to this thing, that's written in terms of x and y, it's equal to this thing. Yeah, and we can do the same for y, for cosine, for sine, sorry. Okay, so we've got this thing written in terms of r and theta. Now we're going to try and use this equation and turn it into something in terms of x and y. And if we get it right, then the thing that we describe should give us the same graph, right? Because, or the same set of solutions, because we are just using different coordinate systems to represent the same actual curve, right? So let's see how this goes. So we have this is equal to this, right? So we have that r of theta, so in this particular case, r of theta over 2 is equal to cosine of theta, right? So we are going to write that as just x over r of theta, like this, because cosine of theta is x over r, right? Like this. So then if we multiply both sides, we have that r of theta is equal to 2 of x, like this. And now we can replace this r with respect to its representation in terms of x and y, and it should be r squared, right? Like this. So then this thing is going to be equal to x squared plus y squared, 2x, and then this is now exactly in Cartesian coordinates, x, y coordinates, and then we can try and mess around with this to get it into a more recognizable form. So what do you recognize from this form so far? What does it look like to you? What does it look like to you? It looks like a circle. Tell me why. But it's not quite the radius because it's times 2x, right? So this x squared plus y squared, if it was some number on the right-hand side, it would be definitely a circle, yeah? But you're on the right track. So, I mean, we see a circle coming out, kind of a circle shape coming out, right? So it's a reasonable guess it's a circle. Yeah, so is there something we can do? I mean, look at this picture. If it is a circle, then it's not a circle around 0, right? This is not a circle around 0, yeah? So what can we do to get this into the form of a circle? And what's the general form of a circle? It's like this, right? It's x squared, x minus a squared, y minus b squared equals r squared. That's the general form of a circle around the point AB of radius r, yeah? So what could we do with this thing to make it look more like a circle? Good. So we can write this, yeah? And then we think, okay, well, then we can complete the square and write this as x minus 1 squared. And if we do that, we'll have this x squared, this minus 2x thing, but we also add a 1, so we subtract 1 to get the same thing, plus y squared is equal to 0, and then that gives us that this thing is this thing. Yeah? Which is exactly the equation of a circle of radius 1 around 1. And let's see out our picture. So, we put 1 here. Then, sure enough, this thing looks like a circle of radius 1, because here it's 2, 0, right? And here this is 0, 0. So it looks like a circle of radius 1 around the point 1, 0. Yeah? Cool. So the picture and the language, the algebra confirm each other. We believe we've done it right. Yeah? We've done it right. Cool. All right. Now, can I raise the board? We have some more topics to discuss. We have to talk about, which is this one. So, cosine of 2 theta. Okay, and looks a very innocent looking equation. Turns out to be surprisingly intricate to sketch it. So I started doing video uploads of classes when the pandemic started last March. So the last part of last year's Calculus 2 course is actually online, and it was asynchronous. So I covered more material, and I did this example, and I actually cut this out and made it a short example. So I will send the link to this. You can also just find it by searching my YouTube channel. But it's well worth looking at this example because this thing of sketching polar curves is one of the harder things you have to learn in this section. And we have a lot of things to think about in this example because as we range theta between 0 and 2 pi, this thing is changing sign a lot. Right, so it's changing sign a lot, so we have to keep thinking about what happens when the radius is positive, what happens when the radius is negative. We use the same techniques for the last example, but it's a more intricate example. We get a more intricate graph. So please watch this example and make sure you follow it. And then you should be set up to be able to do these kind of things in the homework questions and later in the midterm and the final exam. All right, but we're going to skip this, so online already. So my videos back then were much cruder in terms of sound and lighting and whatever, but it's still watchable, I think. All right, so we're going to talk about tangents to polar curves. So, what is this thing about? Well, we sometimes want to do things like figure out the points on a polar curve which has a particular slope, right? Or calculate the tangent line at a particular slope, right? And when we mean slope in this context, we mean the dy by dx slope. So we want to find I put it in quotation marks because it is not the coordinates which we are dealing with, right? Because we're dealing with r and with theta. Yeah. So how do we do this? So we can translate, or we can turn a polar curve into a parametric equation, into a parametric curve. Pretty easily, because a parametric curve is when we have x of t, y of t, or whatever the variable is, right? And if we have a polar curve, then we have that the variable is theta, and we have this r of theta, right? But this thing can be turned into something in terms of x of theta and y of theta. This thing is x of theta, which changes with respect to theta. And this thing here is y of theta, which changes with respect to theta, right? And that thing we can just figure out, right? Because we can just define x of theta to be equal to r of theta. Write that better. The non-dying pen. There we go. R of theta, cosine of theta, right? And then we define y of theta to be equal to r of theta, sine of theta. And as you see, that's going to give us exactly what we want, right? This thing will give us the x of theta, this thing will give us the y of theta. And as theta changes, x of theta and y of theta changes, right? So then we have exactly what we were talking about last time. We have a parametric curve, right? We have a parametric curve. And then we can apply this kind of techniques we've learned before, right? Well, we can apply if we want to. It's generally simpler just to work directly, but the point of this is to show you that we're not going into new territory. We are doing stuff that we've understood before, and that's going to save time in working stuff out. So if we want the dy by dx slope, then we've learned what that is. That is just equal to y of theta over x of theta, right? Previously we wrote it as with respect to t, but theta is just as good a variable. And this thing is indeed the dy by dx slope, yeah? And we just saw the pictures why that's true. And then this thing we can just calculate because we know what y and what x is, right? So if we differentiate y, we're going to have r prime of theta, sine of theta, and then we leave r alone, we differentiate this thing, plus r of theta, cosine of theta. Right? And then if we differentiate the x, same game, just product rule. Overlapping stuff here. Yeah? And then this thing gives us the slope. This thing gives us dy by dx slope. So you could memorize it or way better, just do this, which you see, and then just differentiate, use the product rule, and then you don't get this wrong. And then it's clear, it's natural, nothing surprising, huh? Just what we learned before. And once we have this, and then we can do the same kind of questions about finding where the tangent is certain things, creating the tangent line. And let's do one example of that to finish up with. So this is our example. So I'm only going to do part of it. Given curve, given polar curve, which is defined by r of theta is equal to 1 plus sine of theta. Find the t-line at theta equals pi over 3. All right, so what does this thing look like? So using the techniques we've learned, we could actually sketch this guy. And what does it look like? Kind of looks like kind of looks like this. It's meant to be symmetrical on either side, but it kind of looks like this. And as you get better at sketching polar curves, then you can kind of rather quickly sketch them, simple ones, just like you can sketch curves of simple functions like polynomials, okay? But this thing we can't go into, just spend some time to work this out for yourself, get a rough idea. And then at pi over 3, then it's something like this, right? This is pi over 3. No. Not pi over 3, it's deeper than this. So pi over 3 is something like this. So what we're looking for is the dy by dx slope in order to do the tangent line, which is something like this, right? So in pictures, that is what we're hoping to find. Yeah? Cool. All right, so what are we going to do? Well, we have the formula, then it's just a matter of doing the calculation, right? So this here is our polar curve. This thing gives us our dy by dx slope, yeah? So we just do this differentiation. So the dy by dx slope, just differentiate this expression, is equal to differentiating this. We have cosine of theta and then sine of theta. And then plus this expression, 1 plus sine of theta, cosine of theta. That's on the top, that's the top line, right? And then the bottom, we differentiate this, we have cosine of theta, and then times cosine of theta again, so it's cosine of theta squared, and then minus 1 minus sine of theta, like this. Sorry, 1 plus sine of theta, and then times sine of theta. And that is our theoretic slope at theta, yeah? Just from this formula. And then our job is to clean it up. So let's try and clean it up. So if we factor out a cosine of theta, what are we going to get? We're going to get 1 plus 2 sine of theta, like this. And we are going to turn all of this stuff into sine. Let's do that. So we have this identity, 1 equals cosine squared plus sine squared, right? So then let's write the cosine squared as 1 minus sine squared. Theta equals cosine squared of theta. Let's put that into the bottom. So then we are going to have 1 minus sine squared of theta. And if we multiply this stuff out, what we have minus sine of theta and then sine squared of theta, like this, right? So let's clean it up more. So we have cosine of theta, 1 plus 2 sine of theta. And what we're going to get here, we're going to get quadratic in sine, right? So we're going to have 1 minus 2 sine squared theta minus sine of theta, right? So 1 minus 2 sine squared theta minus sine of theta, and more cleanup. This is a quadratic, we can factorize it, we can have 1 minus and then plus. Yeah. So let's check. So then we get a 1, we get a minus 2 sine squared theta, and then we have a minus 2 sine theta and then plus sine theta. So indeed it gives us exactly this thing. Yeah, it gives us exactly this thing. Cool. And then that is as simple as we can make it, right? There's no further things we can do. And then we just plug in what the angle is. So we have cosine of pi over 3 is equal to 1/2, and sine of pi over 3, and this becomes minus root 3, and this becomes root 3 over 2. Thank you. And then we take this half thing here. Let's clean the space. Let's clean the space. Let's put this up. So we're going to go from here to here. And what we get is we have 1 plus root 3. And then we multiply this 1/2 through. And let's just multiply it on the second part here. So 1 minus root 3. And then we're going to have 2 plus root 3 like this. And then we multiply out the bottom. So this is quite a long story here, but let's keep going. So we multiply the bottom. We are going to have a 2. We're going to have a minus root 2 root 3. We are going to have a positive root 3. And we are just going to have a minus 3 at the bottom here, right? Multiplying the bottom out. And then we have some nice simplifications. Yeah. So then this becomes minus 1 minus root 3. So 1 plus root 3 minus 1 minus root 3. So finally, this is minus 1. Finally at minus 1, which is good because that kind of looks like what the picture tells us. Yeah? That looks like what the picture tells us. Cool. So we finally have the slope. Yeah, we finally have the slope. And then we just need to find the x and the y coordinates of this particular point to actually get the tangent line. Yeah, just get the tangent line. So we can do this too. So we have that x is given by this thing. So x of this particular angle, pi over 3, is equal to r of pi over 3. R is original equation, which I've lost. There we go. There we go. So it's 1 plus 3 over 2 is our radius, and then times cosine of the angle, and cosine of the angle is 1/2. So then this is what our x coordinate is. And our y coordinate is again the radius, which is 1 plus root 3 over 2. Right? This is this thing. And then times sine of this thing, which is root 3 over 2. Yeah? So that's what we are with respect to this point. And then to find the tangent line, we just do the standard thing, right? So the t-line, t of x, it's the slope minus 1, right? X minus the x coordinate, which is this thing. X minus 1 plus root 3 over 2, right? Plus the y coordinate, which is this thing, plus root 3 over 2, 1 plus root 3 over 2. And that thing gives us our tangent line. Yeah? So, in this particular case, the algebra is long, but the actual thing we're doing is straightforward. We know what the formula for the dy by dx slope is, right? I've erased it, but it just follows from writing the x of theta and the y of theta and taking the chain rule, or the product rule, right? So we know what it is. We simply plug in our expression, do the simplifications we possibly can, right? Plug in the value of theta, get out a number, yeah? Check on your graph, if you have time to make a graph, that it's reasonable, that you believe it, and it does look reasonable. It looks like a slope minus 1. And then find the x and y coordinates to actually extract out the tangent line. Yeah? Yeah? And that's it. Okay, and the second part of this question is to find out where the slopes are, whether dy by dx slope is actually horizontal and vertical. It's the same kind of story. We have this general formula right here, right, for general theta. We ask ourselves, for what theta is this thing going to be equal to 0? That would be where we have the horizontal, right? So that will happen when the top is equal to 0, yeah? or where the top is equal to 0 and the bottom is equal to 0, and we have to use L'Hopital's rule. Right? And then we ask ourselves, when is the slope vertical? Right? That's when the bottom is equal to 0 and the top is non-zero. Yeah? Or perhaps where they're both 0, and again we use L'Hopital's rule to see what actually is happening in the limit. Yeah? So the full question is quite lengthy. You will not have a question as hard as this on any exam, but you might for homework. But it is just doing stuff we've done before with this new coordinate system, with a slightly new way of thinking about points in the x and y plane. All right. Thank you for your patience, all of you still here. Any final questions on this before we say goodbye? No, everybody good? All right, have a great day. I will see you on Wednesday, and enjoy the sunshine.